Please join me in congratulating Dr. Cristina Romero Castillo.
Good morning, everybody. I'm so honored to have received this award, and I want to thank the ASLO Board Committee and the ASLO Award Committee. I don't have this. Yes. So I want to also thank the co-authors of this work, who are Maria Pinto and Teresa Langer from the University of Vienna, Pepe Álvarez Salgado from the Instituto de Investigaciones Marinas de Vigo in CSIC, and also Gerhard Händel from the University of Vienna. First of all, I want to explain you how I am doing this work, because my background has been always the biochemistry of the dissolved organic matter. So when Lindemann proposed this diagram of the trophic cycle in 1942, he placed in the middle this ooze that he defined as a non-living nascent matter. But at that moment, the dissolved organic matter was not that known. So I'm pretty sure if today he would have added to the dissolved organic, he would have added to this ooze the dissolved organic matter as part of this ooze. So that he defined first was a kind of detritus, and I think we could add now this DOM, dissolved organic matter. So I'm so interested on the dissolved organic matter because this has been accumulating in the ocean for thousands of years until built an amount of 700 gigatons of carbon. This amount is similar to the amount of carbon in the atmospheric CO2, and since they are connected, both pools, through the carbon cycle, any little change in one of these pools will affect the other and the climate. So I was very intrigued to know why this matter is accumulating, which are the sources, the sinks, and the dynamic and the distribution of this matter. So here we have several cruises from the US repeat hydrography, where we have the DOC observation. We can see that in the Southern Ocean, the carbon is very low. Then we have medium values in the subtropical gyres and highest values in the tropics. So I wanted to understand why the DOC distribute in this way, what controls that distribution. And to answer that, I went to work with one of the best experts on this topic in the world, who is Dennis Hansel in the University of Miami, in Rasmus. So we wanted to understand what was driving this distribution, and we found that the nutrients reaching the euphotic zone from the deeper layers were controlling that distribution of carbon in the surface. So we made a simple model using nitrate from deeper layers to get the DOC accumulated in the surface, and we map it in the Atlantic Ocean. So here we have the background of this map is the calculated DOC, and the overlapping dots are the observations. So the model fit very well, but there was an area in the west of the North Atlantic subtropical gyre where it didn't fit very well. So here we can see it better. We plot the DOC calculated versus the observation DOC, and we see that in the North Atlantic subtropical gyre, the samples go out of the line. So we had an excess of 13 micromolars of dissolved organic carbon that we couldn't explain with the nutrients coming from the deeper layers. So we were thinking, what could explain that? So we tried different options. So maybe it's atmospheric deposition that is bringing also nutrients. Maybe it's nitrogen fixation. Maybe evaporation. So we tried all of these, nothing worked. So we didn't know. So I was close to give up on this. Dennis told me, Cristina, you cannot give an explanation to everything. Just go on with your work. So I was close to give up on that, when suddenly, by coincidence, a guy came to our university, in University of Miami, to give a talk. And he was a physical oceanographer talking about plastic drifting in the ocean. Like, he made a model showing how plastic accumulates in certain areas. And I didn't know that guy at that moment, but it turned out to be Eric Van Seville, who had a wonderful talk yesterday. So when I saw this map, I'm so glad that I went to that talk back in the University of Miami, because when he showed this map, I saw that the area of the west of the North Atlantic subtropical gyre, where he said that plastic accumulate, was coinciding with the area where we were seeing the excess of carbon. So I thought, what if it's the plastic that is releasing all this carbon and making this excess? So yeah, because we know that plastic are polymers that are never pure. Usually they have additives like antioxidants, plasticizer, colorants, to give the plastic the properties required for its use. And also, these additives could migrate to the media. For example, we have the example of the bisphenol A, the BPA. Maybe you know that, because it was very controversial some years ago. This compound was used in food and drinks plastic containers. And it was known that it was migrating to the food, and it turned out to be like endocrine disruptor, cancerogenous, and very harmful. So at the end, it was forbidden. So I thought, okay, if we have 250,000 tons of plastic floating in the ocean, could be this plastic also releasing carbon, like that could be contributing to the VOC pool that we have in the ocean? So I wanted to try that, but there was a problem. Is that my contract with Dennis was finishing in the University of Miami, and I had to leave the US. So I couldn't try there, but I cannot complain, because I was very lucky, because I was contracted by Gerhard Händel in the University of Vienna. And I proposed him this idea, and he liked it, so we started to do a series of experiments, a lot of experiments, to test this. And we use different types of plastics, mostly polyethylene and polypropylene, which are the most common plastic found in the ocean. So we did high-density polyethylene and low-density polyethylene and polypropylene. It was plastic new from commercially available, but also from supermarket, like basket or bags. So we put the plastic on artificial seawater, because we want that the media had the lowest amount of carbon possible to can see the leaching. And we put this plastic on the seawater and on quartz tubes, so we could irradiate it with UV visible radiation to simulate the sunlight. And we also did dark treatments, and we also did treatment controls without plastic. So very important, the water we used was sterilized, autoclave, to be sure that we didn't have bacteria, because we wanted this experiment to be abiotic. So we incubate this for different time of period, and we measure the dissolved organic carbon before and after, and also bacteria at the end of the experiment to be sure it was arsenic. And here are the results. So we have, this is the DOC leached from plastic, normalize it to the plastic surface that we put in every flask. And so it's in microgram of carbon per square centimeter. And we have here different period of incubation, and in all of them we found that plastic was releasing DOC, dissolved organic carbon. And we didn't see a clear pattern between light and dark treatment. Sometimes light was higher, other times dark was higher. So we found at the end this range up to 9 micrograms of carbon per square centimeter. So we want to extrapolate this to the global ocean and to know if this was how much carbon was released from the whole amount of plastic that is floating there. So for that, we took the values from Jan Beck et al. In 2015, who said that in 2010, up to 13 metric tons of plastic entering the ocean. So using this range that they gave, and also using the density and average density of the plastic and our values from our experiment, we found that 20 3,600 tons of VOC is leached from plastic into the ocean every year. So someone could say, well, but comparing this amount with the 700 gigatons you have in the VOC pool, maybe it's not that high. Well, but if you go to the surface microlayer, where this plastic is released, in very polluted areas, like the subtropical gyres, up to 10% of the VOC in the surface microlayer could originate from plastics. And where all this carbon goes, which is its fate. So we know that VOC in the ocean is mostly consumed by bacteria. So we wanted to know if this carbon from plastic was also labile for bacterial uptake. To do that, to test that, we did another experiment in which we took the plastic leachate from the previous experiment, and we removed the plastic pieces, and we add a natural bacterial inoculum. And then we incubate this during several days until bacteria reach the exponential phase. And we did this with all the treatment, the light, the dark treatment, and also the control without plastic. And we found, this is the bacteria abundance, we found that in all the treatment with plastic, at the end of the growth curve, the density of bacteria was higher in the plastic treatment regarding the control. Interestingly, we also found that the dark treatments, in the dark treatments, bacteria start to grow earlier than in the light treatment with plastic. We also found this nice correlation in which we found that those treatments where the leaching was higher, the consumption by bacteria was also higher. So that means that bacteria were consuming the VOC from the plastic, and the slope of this relationship tells us that at least 50% of the carbon released from plastic was consumed by bacteria, was labile for bacterial uptake. And we also saw that in the slope is higher in the dark treatments, meaning that in the dark treatments, those that were not previously irradiated with the plastic, the consumption by bacteria was a bit higher than in the irradiated treatments. So to conclude, we found that plastic leachates VOC into seawater, that up to 23,600 tons of carbon can be released per year from plastic, that VOC leached from plastic stimulate microbial growth, and at least 50% of that carbon is available for microbial uptake. So if we go back to Lindemann diagram, that he didn't know when he proposed it, is that 60 years later, we would have to add another kind of detritus to this ooze, new detritus, our detritus, that is anthropogenic, that is micro and nanoplastic, that are also entering in the trophic cycle. To end, it's only let me to remind you to not forget to reuse and avoid waste, because even if you use biodegradable or compostable plastic, they don't degrade in the ocean. They need high temperature that are not reached in the ocean. And then even if you recycle or compost or whatever, it has an environmental impact that is higher than if you don't generate that waste. And that's all I want to explain you, and thank you for your attention.